Good evening. Today we're going to be discussing the tension and the energy of a stretched MILF string. Now, before we begin with that, we need to talk about something called the static gauge. And it's sort of our way of simplifying the formulas, right? So, um, so, okay, before we get into the static gauge itself, first you guys need to know that, or you guys would know from field theory or quantum field theory or from gauge theory that the action S for a particle is reparametrization invariant. So if I choose some new coordinate system wherein my action is essentially setting on, it would stay the same. So suppose that this is my world line for a certain particle, P, and this is suppose this is my first coordinate system x1, and then I perform another reparametrization into some, no, not x1, but rather some x, and then I do reparametrization to a coordinate system x prime. What you guys would know is that even though it looks different, so even if the line looks different or the world line of the particle looks different, the action computed from this over here, so integral of the Lagrangian dt, and then so so let's say that this is S1. So the action computed from the Lagrangian over the coordinates in this coordinate system, and let's say S2 is is then the integral of the Lagrangian with respect um, to the new coordinates. What you guys would know is that S1 must equal S2. So you can actually prove that by reparametrization, re doing a reparametrization over the nambu goto action. So you find with that for some reparametrization over the nambu goto action, it would be equal to the original nambu goto action in our usual coordinates. Our tau sigma coordinates, and that's what's important. It's invariant in reparametrization. And in fact, you guys would know that reparametrization is an example of a gauge, essentially. So what we do with gauge is either we add dimensions or we do some mathematical techniques, maybe exploit symmetries in the fundamental structure of our mathematics, such that our calculations become more simplified, right? So um, in fact, reparametrization here in string theory is analogous or it's similar to gauge invariance in electrodynamics, right? Um, you guys would know that there are symmetries, right, when it comes to electromagnetic phenomena. So, um, so the like for example, the Maxwell's equations essentially are gauge invariant, so to speak, um, and they have symmetries. They possess symmetries under gauge transformations that lets us use different potentials to represent those electromagnetic fields we're studying. Um, so just like we can use different kinds of potentials in our study of electromagnetic fields, we can choose different choices of parameters, which would be useful in our study of these phenomena in string theory. So instead of a total parametrization or total reparametrization of the coordinates, we're going to talk about a partial reparametrization, which is called the static gauge. So the static gauge is that, so if x is um, my string function, or m, so mu of my sigma tau, then the static gauge is then gives, so I'm gonna set, okay, no, uh, in the static gauge, So in the static gauge, um, uh, what we want to do is fix the lines of constant tau by relating tau to the time coordinate. So we're gonna do some relation tau, so some relation to x mu not x mu 0, and that is simply equal to c times ct, or c x0 essentially. Okay, in some chosen Lorentz frame. So in our parameter space, so let's say this is my parameter space, this is my sigma, and this is my tau. We consider various lines of hyperplanes. So this is really just a one-dimensional example or two-dimensional example. So we're considering lines in it, but really, when we're talking about d-dimensional space-time, right, and multiple parameters, we're talking about hyperplanes. So we're going to consider these hyperplanes t equals t0 in the target space. So for these lines over here, there is an associated sort of line that runs along, so a bunch of lines in our target space that run along the world sheet of my string. So there are corresponding strings, or let's say this is a section. There are corresponding hyperplanes, like go like this. So each of these lines over here are mapped to a hyperplane inside our d-dimensional spacetime. Okay. So through this, we also have to declare, so we declare that for some point Q, so let's say this is a point Q on the world sheet, I'm use P, okay, let's use P. We declare that for any point P on the world sheet, so tau of P, so the time coordinate of P, be equal to T of P. Okay. So again, this choice that I have chosen is the static gauge. So this is still the static gauge, and so in this static gauge, okay, so we have chosen a sort of restriction for tau, but how about for sigma? So what are the restrictions for sigma? We're not really going to touch sigma much, but we do know that for an open string, sigma would be restricted to 0 and some sigma 1, essentially. So for an open string. For some closed string, I'm pretty sure that your sigma would be part of some 0 to 2 pi, right? Because we know that sigma would be part of essentially R mod 2z. And this is for a closed string. And we have had some discussions on whether we should classify certain types or associate certain types of fundamental MILF strings to, or associate MILFs to either an open string or a closed string, but we're not quite sure yet if the physics would work out. So we'll just see how that works out in the end later on, or much later on in the development of the physics. Okay, so So if I want it to be closed, so for the closed string, essentially I want it to be a circle, right? So this is an open string, right? This is an open string essentially. Say it's a section of it. And this would be my closed string. It would have to be some loop, some closed loop. And in order for it to be a closed loop, I need to make some identifications, right? So I need to associate points as the same on my world sheet. And in order to do this, to keep it topologically a cylinder, essentially, so to speak, if I want for a certain circumference, so let C be the circumference of the, say, the world sheet cross section, then I need to make the following identifications. So identify the points tau sigma to oh no, that's not identification. I'll do it in my notation. So sigma tau is identified with my sigma plus C, and then the same tau. Now in the static gauge, of course, I would then have that my sigma tau is equivalent to sigma plus C and then some T, right? That's my static gauge for some hyperplane T. So now, because of this, it would then hold that my sigma will be restricted to a certain 0 up to C for the closed string. So now that we've discussed sort of the topology of things, what does our identification mean? So what does our declaration hold for the physics? So we have said that m0 of tau sigma is equal to Ct T of tau sigma, and that's equal to C tau. So we have made that declaration. So we have set this sort of T equals to tau itself, or simply tau is equal to T, or defined to be T. So what does that mean? So what that means is that we can describe the collection of our string coordinates, so everything that we know about our string, so mu, as the following. So I can say that mu tau sigma is then equal to mu T sigma, and that is essentially the set. Oh, no, it's the vector. So C tau, and then this is my spatial component of my MILF string. It's still a function of T and tau. So if I let this vector over here represent the spatial string coordinates, so spatial string coordinates. So with this, we find out that the equations of motion, so we then find out that the derivative of my MILF string with respect to my sigma is essentially equal to what? So that would be m0 with respect to sigma, and then m, so the spatial component with respect to sigma, and we know that this would have to be 0, so then my triplet becomes 0 and then del m spatial by del sigma. And for tau, the spatial component vanishes, or rather all other derivatives of the spatial component vanishes apart from the T component. So del MO by del sigma. Oh no, it becomes T, so my bad. It becomes T and then del M spatial by T. And that's equal then to C and then del m spatial by dt. We're only left with one. No, we still have all the coordinates. However, we're now talking about a time derivative. Oh wait, this is time, by the way, not sigma. My bad. So this is with respect to tau. And because we chose the static gauge, we would set that tau equals to t for some varying t. It would essentially be this. I would get this result. And it makes sense because when I take the derivative of m0 with respect to t, I would be left with just c, because recall that the spatial component is simply c tau or ct. Okay, so you could do a test with the nambu goto action. When I do this, that you would get the same value, essentially. Yeah. Okay. So if you plug things in and you do the computation, so in the computation square root of negative g, you would find that it would be equal to the square root of 0 minus del m spatial by del sigma squared times negative c squared. And as you can see, we don't get any negatives under square root because this cancels out with that. Even we would simply c squared del m spatial by del sigma squared. And that's good. That's good because then I would get c del m del sigma, which is again good. And you guys will notice later when we actually do computations with the nambu goto action that this is a good thing. This is a good thing. And it will explain why later when we try to compute the tension and the energy of a stretched MILF string, we're using the static gauge. So if you guys see how useful the static gauge is. So now let's move on to tension and energy. For this example, we're going to be considering a is it massless? I don't know if it's massless. So considering a non-moving. So we're going to consider a non-moving string. And because it's non-moving, the Lagrangian is essentially just the potential energy. Okay? Because usually if it's moving, we would have to consider a non-zero kinetic energy term in the Lagrangian. And we will discuss that for another lecture. Or we'll discuss that in another lecture. So we'll consider the one where the Lagrangian is simply equal to the potential energy. Okay, so far so good. So next, we're gonna stretch the endpoint of the string up to some point A. So for some origin on the world sheet or the string, we're gonna stretch it out up to some point A. And let's say this is the world sheet, the actual world sheet of the string. And we're also going to be considering an open string for the time being because the certain identifications we've made for a closed string would pose a different kind of computation or give me a different kind of action. Okay, so from our parameter space, in our parameter space, I essentially would have some. Okay, I would have some 0, so sigma equals 0, up to my sigma 1. So that's why I also talked about that, because the notation helps with understanding what our static gauge would imply when computing the tension of the stretched string. So via my m mu function, I would map these points up to my I think. So this over here is my sigma axis. That's my tau axis, and through my mu, my m mu function, we map those coordinates onto their respective coordinates on the world sheet. Okay. So what we want to assume next is that the rest of the coordinates vanish. So next is the rest of the coordinates vanish. So that's our second assumption. So first it's that it's a non-moving string. Oh no, it's technically the third. The second is that we stretch the string from some 0 up to distance a. And then we next assume that the rest of the coordinates vanish. Okay. So, of course, when they vanish, I would then denote the endpoints in some coordinate system to be 0, and then the 0 vector in our d-dimensional coordinate system. And the next coordinate would be 0, and then a. No, a then 0, my bad. So these are the coordinates, essentially. So the actual absolute coordinate would be 0, and then the 0 vector in d-dimensional spacetime. And then, my bad, the notation's pretty bad here. A doesn't have the vector, it is its own value, but rather the 0 vector. Okay, so A, then the 0 vector. Okay, just so we're on the same page on when it comes to describing the coordinates 0 and a on the world sheet with respect to the actual coordinate system where the string lies in. So this 0 vector is the 0 vector in the d-1 dimensional spacetime. So if the ambient spacetime is d-dimensional, then my 0 vector is inherently d-1 dimensional. Okay? So what this ensures is that the string is not stretched in any other direction apart from in the direction of A. Okay? So again, because we assume that all the other coordinates vanish, then it would hold, I keep accidentally pressing that part, it would hold that my M2 and then my M3 and then up to my MD are equal to 0. Okay? And for each sigma inside here, so let's say this point over here, there is an associated f of sigma on the world sheet. Okay, so again, this is some reparametrization I'm doing. So I then have some function, so some f that maps my parameter space, so that maps sigma tau to my mu sigma tau, and this f particularly only maps sigma, so it doesn't really map my tau, but rather the set of all my sigmas. Okay, and m of sigma, not really of tau only. Okay, so this only maps it onto a sigma. All right, so what are the rules for this function? So the sigma, this f of sigma would be equal to a when my sigma is equal to sigma 1, and f of sigma would simply be 0 when sigma is equal to 0. Okay, so essentially this point over here, A, is described as the spatial vector A and then 0. The 0 vector would essentially be my f of A. So this over here, f of sigma 1 And this zero, this point zero on the world sheet would be my f of 0. Okay. So not only do we have a mapping from the parameter space onto the world sheet via m, but rather we have another function that maps these two endpoints, or any point, any guy on this line onto this line over here. Now next we require that f is strictly increasing. Okay, so f is strictly increasing. Now, why do I want it to be strictly increasing in this interval over here? And the reason why I want it to be strictly increasing is that for each point, so we already know this is some sort of bijection, right? So each point over here, so each sigma in this interval is mapped to a unique f of sigma on this section of the world sheet. Okay? So there's that, or on the string, essentially. So from that, it also follows that the derivative, so the derivative of f with respect to sigma must be greater than 0 because it's strictly increasing. Okay? So moving on, it follows then that my m dot mu is equal then to c, the speed of light, 0, then the 0 vector in our d minus 1 dimensional spacetime, and my m prime mu is equal to 0, and then f prime, and then 0 vector. Wherein, of course, this means, so m dot means the derivative of my m with respect to the tau coordinate, and m prime is essentially my derivative with m with respect to the sigma coordinate, and of course f prime means the derivative of f with respect to sigma. Total derivative, so we don't need the partial derivative sign. Okay, so following from that, we also know then that you can then compute that, so m dot squared is equal to negative c squared. M prime squared is then equal to f prime squared, and you could also compute that the m dot contracted with m prime is 0. So using this is the information we essentially need to compute our action. And it's all thanks to the static gauge, because we assumed over here, so essentially here in this section, in the beginning, we assumed the static gauge. And recall that's my c, my x equals, or my m equals ct, essentially, c tau. And that will come in handy later. So recall that the nambu goto action, so the nambu goto action is equal to negative initial tension divided by c, the integral of dA, it's the area element. And essentially, if in expanded form, this is negative dO divided by c, integral with respect to some tau 1, tau 2, d tau, integral from 0 up to sigma 1, d sigma of the square root of negative g. And of course, the negative g would then be equal to combinations of these three facts. So you then find that. So we find that nambu goto action reduces to something of the following form. tau 1, tau 2, d tau, integral from 0 up to sigma 1, d sigma, square root of, so this is 0 minus negative c squared and f prime squared, because this negative g would essentially be, so this would be, m dot contracted with m prime squared minus m dot squared contracted with m prime squared, right? So I get the following expression. The negative cancels out, and this is because we use the static gauge at the beginning. There, it's finally showing its usefulness. And this reparametrization ensures that I get to cancel out these squares, essentially. So it's a good thing we use the static gauge in this case, because if we didn't, we might have ended up with a negative under that integral sign. So, going back to the integral, I get tau 1 to tau 2, d tau, integral from 0 to sigma 1, d sigma. So the squares cancel out with the square root, leaving me with c squared f prime. And f prime, so c squared I can bring to the front and it would cancel with the c. Oh no, the square would go away. Sorry, my bad. C f prime. And the c would cancel with the c at the front. So it becomes, so the action is negative to integral from t1 to t2 d tau, integral from 0 to sigma 1 of d sigma, and this f prime is a total derivative. So from the fundamental theorem of calculus, I can reduce this into simply just an expression involving f. So the integral goes away. To integral from tau 1 to tau 2 d tau, and then essentially this would be f of sigma 1 minus f of 0. But we know f of 0 is 0, so that vanishes. And we know that f of sigma 1 is essentially a, so I can replace it with a. And a is a constant, and I can pull it out. So negative to a integral from tau 1 to tau 2 of d tau. And again, the value of the action does not depend on my reparametrization. So it would still be the same for any choice of f over here. So, okay, so if I put this inside, if I put my TOA inside, it would be essentially T1, T2, negative TOA dt. And we know that the action is the integral over some T1, T2 of the of the Lagrangian with respect to t. So we know that the Lagrangian in this case, we assumed in the beginning it's simply just the potential energy. So we know that this expression, if I compare it, this expression is essentially my Lagrangian, which is also my potential energy. No, actually it's minus V, because my minus BE, because my kinetic energy vanishes, it would be negative BE. So then the Lagrangian would be equal to TOA. And my potential energy would also be TOA. So there it is. So for some string tension TO, which you can compute via Hooke's law or something, any approximation you want, and to some point A where it has been stretched, these are the values for the Lagrangian and the potential energy. Now you can also consider the sort of length density, right? You can also consider the rest mass per unit length or the rest mass per unit density. Um, but really, it just confirms that the minus sign in the front of our action, so this one over here, um, it just tells us that that is necessary. Otherwise, the potential energy of our string would become a negative. Okay. So this sort of small computation we did with the nambu goto action tells us something important about my m dot and my m prime functions. It tells me that they don't depend on tau. Okay? It tells me that they don't depend on tau. And because they don't depend on tau, my momentum function, my momental function, so my p, so really I had two versions. It wasn't just a p that I used to derive something else, I believe, from the last lecture, but there are two versions, one for tau and one for sigma. The one for tau, one for sigma. And these also do not depend on tau because their constituents are essentially combinations of my m dot and my m prime, which also don't depend on tau. So because of that, this also doesn't depend on tau. Okay. So because these two functions, my momental functions, are independent from tau, it makes sense that when I take the derivative of any of these, so sigma mu, it would essentially be 0. Oh, that's a very goofy color. And it also requires, so this sort of thing that we have concluded also requires that our function over here is a sigma independent. So you find then that the p sigma mu is equal to my negative TO over C times my C squared M prime mu over the square root of C squared F prime squared, and that's then equal to negative TO M prime mu over F prime. And don't be confused by the index mu, we're simply talking about spatial components, but in the lower index. Okay. So this only works for mu. So this expression over here only works for mu not equal to 0. If it's not equal to 0, I would require that my boundary condition would satisfy the free boundary condition. So for m equals 0, I would require that p sigma 0 would be equal to 0. Okay. So that's really it when it comes to the energies and the potential energy and the Lagrangian of or tension of my stretched string. Again, I had to discuss the static gauge in the beginning because again it really helped a lot with the computation in the following discussion because it eliminated that negative inside the square root essentially. And it was also pretty neat that there's a negative in front of my action because that also ensures that my potential energy and my Lagrangian are non-negative. But of course, there are certain instances in physics, especially when we discuss about the Dirac equation, that we will end up with some negative energies. It's unavoidable that there are objects out there, particles or whatever, entities that contain negative energies. And I'll give you guys a hint already for the next lecture. We're gonna divert a little bit from we're gonna divert a little bit from string theory, and we will go into some quantum field theory. But what I want to leak to you guys is that everything we know has some sort of polar opposite, so to speak. So just like how matter has antimatter, our stuff, so the stuff that we know, we've been discussing throughout everything in physics, has anti-stuff. So essentially stuff that have the same energy but reverse the sign, right? Same charge but different sign. So an example would be the femboy, and the counterpart would be the tomboy, right? That makes total sense. And these stuff are derived from the Dirac equation. Okay, and yeah, that's sort of a thing. You will end up with some stuff. So even though in our example right now, our string itself has positive potential energy in Lagrangian, the stuff that it generates or the stuff that comes from it, um, so these matters or these stuff could end up having negative energy, and that's all due to the Dirac equation. And this would be, it's a D, that's a D, that's a D by the way, not a P. And that will be the discussion for next time. So until then, I'll see you guys. So cheerio until then.